In question 1, we've got the curve here C, and we need to show that the x-coordinate of the stationary point satisfies this given equation here. So I will start by differentiating. We've got y is x squared cos of x over 2. I'm using the product rule of differentiation here. So dy dx is 2x cos of x over 2 plus x squared times the derivative of cos of x over 2, which is minus a half sine x over 2. We set this equal to 0 as it's a stationary point. I can divide throughout by cos of x over 2 to get tan into the game. So we divide everything by cos of x over 2, and this leads to 2x minus a half x squared tan of x over 2 is equal to 0. I can now factor out the x, so we've got x brackets 2 minus a half x tan of x over 2 is equal to 0. So either x is 0 or 2 is equal to a half x tan of x over 2. Now x is 0 is rejected because we were told from the beginning that x is strictly greater than 0. So I reject the solution of x is 0, and I concentrate on 2 is a half x tan of x over 2. I cross multiply, I get 4 is x tan of x over 2. I divide by x to get 4 over x is tan of x over 2. And I can take arc tan of 4 over x is equal to x over 2. And therefore I get 2 arc tan of 4 over x is equal to x as required. In part B, we need to use the given iteration formula to find the value of x2 and x6. Now remember that x is in radians in this case. So we just use the calculator, we store the initial value of x1 being 2 on our answer key, and we continue pressing the equal sign to get that x2 is 2.214, x3 is 2.130, x4 is 2.163, x5 is 2.150, and x6 is 2.155. In question 2, we start by showing the given identity here. I will start from the left-hand side. We've got on the numerator 1 minus cos 2x over 2 sine of 2x. So I will choose a double angle identity for cos 2x that goes in the form of 1 minus 2 sine squared x. This will allow the 1 to cancel out with the 1 here. And in the denominator, sine of 2x is 2 sine x cos x. And therefore, we've got in the numerator 2 sine squared x. And in the denominator, we've got 4 sine x cos x. Now we can simplify the sine x in the denominator with one of the signs in the numerator. The 2 with the 4 leaves me a 2 in the denominator. So all in all, this is a half of sine of x over cos x, which is of course a half tan x, which is the right hand side with k being a half. And then it says he can solve the given trigonometric equation. Theta is in degrees between 0 and 90. So we know that this part here can be replaced with a half tan theta. So let me start by writing the given equation, and then we will proceed. So 9 brackets 1 minus cos 2 theta over 2 sine 2 theta is equal to 2 sec squared theta. So 1 minus cos 2 theta over 2 sine 2 theta will be replaced with a half tan theta. And this means we're looking at 9 over 2 tan theta is equal to 2 sec squared theta. It makes sense to get rid of the denominator, so I will say that 9 tan theta is 4 sec squared theta. And then we've got an identity that connects sec squared and tan squared. We know that sec squared is 1 plus tan squared. So what I have at the back of my mind is that I'm trying to get a quadratic in tan. So expanding the right hand side is 4 tan squared theta minus the 9 tan theta that was on the left hand side plus 4. And I can now use the quadratic formula to get values for tan theta. So tan theta is minus b plus minus b squared minus 4ac square root of this, and all of it over 2 times a, so 2 times 4. So this is giving answers for tan theta of 9 plus minus root 17 over 8. So why they have that tan theta is 9 plus root 17 over 8, which gives me theta to be 58.6, or we've got that tan theta is 9 minus root 17 over 8, which makes theta be 31.4. These are the only solutions between 0 and 90, so 31.4 or 58.6. In question 3, the first part, we need to find this indefinite integral here. So we've got the integral of 12 over 2x minus 1 all squared dx. So the first thing to do is get the 2x minus 1 in the numerator and write as 2x minus 1 to the negative 2 dx. Since the expression within the bracket is a linear one, I can simply increase the power by 1, divide by the new power, and also divide by the derivative of the bracket, which is 2, plus the constant of integration. Now this simplifies to minus 6 over 2x minus 1 plus c. In II, the first part is to write 4x plus 3 over x plus 2 in this form here, and then use algebraic integration to find the exact value of this integral. Now, the 4x plus 3 over x plus 2 is an improper integral because the degree of the numerator is 1, the degree of the denominator is also 1, so I can use long division to proceed here. So we've got 4x plus 3 divided by x plus 2. So we know that we need to match the highest order term on the left. So x will be multiplied by 4 to give me 4x plus 8. I deduct. I have a remainder of negative 5. And therefore we have that 4x plus 3 over x plus 2 is equal to 4 minus 5 over x plus 2. This was a necessary step in order for us to proceed into evaluating the integral here. Notice the hence after all here, which means that we need to use our answer from part A. So let's see. In part B, we need to integrate from negative 8 to negative 5, 4x plus 3 over x plus 2 with respect to x. So we write this as the integral from negative 8 to negative 5 of 4 minus 5 over x plus 2 dx. The integral of 4 is 4x. The integral of 1 over x plus 2 is simply ln x plus 2. I put the modulus sign, the absolute value there, and I go from negative 8 to negative 5. I will now substitute the upper limit to get 4 times negative 5 minus 5 ln of minus 5 plus 2. I put the modulus sign there, minus 4 times negative 8 minus 5 ln of the absolute of negative 8 plus 2. So 4 times negative 5 is negative 20 minus 5 ln of 3, because minus 5 plus 2 is negative 3 and its absolute value will be 3. Then this is negative 32, and with a negative here it becomes a plus, so plus 32. And I've got again negative with negative makes a plus 5 ln of 6, because negative 8 plus 2 is negative 6 and its absolute value will give me 6. Now negative 20 plus 32 is 12, and we've got 5 brackets ln 6 minus ln 3, which is 12 plus 5 times ln of 6 over 3, which simplifies to 12 plus 5 ln 2. In question 4, we've got the function f of x here and g of x, and we need to solve the equation f of g of x is 3. So it's a composite function, so we first need to do g of x and then input it to f. So we've got f of 5 minus 2x squared is equal to 3, which takes us to 4 brackets 5 minus 2x squared close brackets plus 6 over 5 minus 2x squared minus 5 is equal to 3. We could expand the numerator, we'll get 20 minus 8x squared plus 6 over minus 2x squared is equal to 3. So I could now cross multiply to get 26 minus 8x squared is minus 6x squared. So collecting everything on the right hand side, 0 is 2x squared minus 26. So we've got that 26 is 2x squared, which leads to 13 being x squared. So we have that plus minus root 13 is equal to x. However, if we look at the domain of g can only accept as input non-positive values for x, so x has to be less than or equal to 0. So I could have never started with x being plus root 13. So we can say that since the domain of g is all x less than or equal to 0, then we can only conclude that x must be minus root 13. In part B, we need to find f inverse. So we start by writing out that y is equal to 4x plus 6 over x minus 5. We interchange x and y, which leads to x is 4y plus 6 over y minus 5. We can cross multiply to get that xy minus 5x is equal to 4y plus 6. So I will collect all the y's on the left. So xy minus 4y is equal to 5x plus 6. Let's factor out the y. Y brackets x minus 4 is 5x plus 6. So y is 5x plus 6 over x minus 4. This is the expression for f inverse of x. So f inverse of x is 5x plus 6 over x minus 4. However, we are not done. We also need to find the domain of f inverse, and we know that the domain of f inverse will be the range of f. So that will be my starting point. So domain of f inverse is the range of f. To find the range of f, I will actually sketch f of x. Now recall that f of x had the equation y is 4x plus 6 over x minus 5. We've got a vertical asymptote at x is 5. It's the point at which we've got division by 0, and therefore the function is undefined. For the horizontal asymptote, we need to consider the behavior of y as x tends to infinity. So we can say that the plus 6 and the minus 5 are insignificant when x grows really large. And so y goes to 4x over x, or simply 4. And so the horizontal asymptote is at y is equal to 4. So the next thing to do is find the cuts on the axis. So when x is 0, we can see that y is minus 6 over 5. And when y is 0, we've got 4x plus 6 is 0. So 4x is negative 6, which leads to x being minus 3 over 2. So we now have enough information for us to sketch the function. So we had an asymptote at x is 5 and an asymptote at y is equal to 4. So this is y is 4, this is x is negative 5. We've got cuts on the negative y and the negative x-axis, so it will look something like this. So this is the minus 3 over 2, this is the minus 6 over 5, and similarly we've got this part here. Now, we were told that f of x was defined for all values of x apart from 5. So no other restrictions here, and we can see that the range of f is y belongs to the reals apart from 4, and that's the domain of f inverse. So to conclude the answer to part B, we say x belongs to the reals, x not equal to 4. In part C, we need to sketch and label g of x and g inverse of x. So to do that, we will start by considering the graph of g of x, which was defined to be 5 minus 2x squared for x being less than or equal to 0. So let me write down the equation for g of x. It's 5 minus 2x squared, and we've got x less than or equal to 0. We can see from the equation that g of x is always less than or equal to 5. The shape will be an inverted parabola, so it will be like something like this. I will set g of x to be 0 to give me 0 is 5 minus 2x squared. So 2x squared is 5, leading to x squared being 5 over 2, and x is plus minus the root of 5 over 2. However, because x has to be less than or equal to 0, we know that we can only accept the negative solution. The x is minus 5 over 2 square root. So let's put g of x on the graph, and then let's consider how we derive the shape of g inverse. So there we are, we've got g of x here, we've got the maximum at 0, 5, we've got the cut on the x-axis at minus root of 5 over 2. We know that the graphical relationship between g of x and g inverse is that one is a reflection of the other along the line y equals to x. So I draw my mirror line, and then the cut on the y-axis will become a cut on the x-axis. The cut on the x-axis will become a cut on the y-axis, and any point that lies on the mirror line will remain exactly there. So g inverse of x should look something like this. There it is, the cut on the x-axis is at 5, the cut on the y-axis is at minus root of 5 over 2. This is the graph of g inverse. You can see the symmetry along the line y equals to x. In question 4, we have a graph of log a base 10 against t. It's a straight line with these 2 points given. We know that the model is of the form a is pq to the t, and we are asked to find to 3D p's the value of p and the value of q. So I will start by finding the gradient of this straight line. We're using y2 minus y1 over x2 minus x1, so 0.56 minus 0.32 over 8 minus 0, which gives a gradient of 0.03. So on the vertical axis is log a, so that's my y. Log a base 10 is 0.03t plus 0.32. That's the equation of the straight line. On the other hand, we've got that the model is of the form a is pq to the t. So if I take logs of both sides, I get log of pq to the t base 10, which can be written as log of p base 10 plus log of q to the t base 10. And therefore, log of a base 10 is equal to log of p base 10 plus t log q base 10. And I can now compare coefficients. The 0.03 is what appears in front of t, and the 0.32 is what is the constant here. So I will set the log of q base 10 to be equal to 0.03 and log of p base 10 to be equal to 0.32, which means that q is 10 to the 0.03, which gives me an answer of 1.072, and p is 10 to the 0.32, which gives an answer for p of 2.089. Now in part B, we are being asked to use the values of P and Q to find the rate of increase of the surface area in square meters per day, exactly 6 days after the start of the study. So I will start from the form of the original model. I'm not substituting numerically the values I found for P and Q, as it will make it a lot more difficult to keep track of all the numbers. So dA dt, well, P is a constant, it's just there. The derivative of Q to the T is Q to the T ln Q. So what I'm using here is the rule which says that if y is a to the x, then dy dx is a to the x ln a. So in this case, the x is the t and the a, the base, is the q. So we have the expression for dA dt, so we will evaluate this when t is 6. I will now substitute the value for p, 2.089 times 1.072 to the power of 6, ln of 1.072. Plug everything on the calculator, we get 0.22 square meters per day. In question 5, we are told to produce two separate diagrams, one for each of these graphs, and we need to show in terms of k where we cut the axis. So we start with y is k minus 2 modulus x. It's a good rule of practice if we try to express the graph without the modulus sign. So it's going to be k minus 2x if x is greater than or equal to 0, and it's k plus 2x if x is negative. So as a quick reminder, if the input, in this case x being greater than or equal to 0, is positive, then the modulus sign behaves like a normal set of brackets. If it's negative, the input is negative, then the sign outside changes. So this also helps us in identifying the position of the vertex. The vertex is when x is 0, and when x is 0, y is k. So I could draw a pair of axes here. I will start by pinpointing the location of the vertex. So there it is, the x and the y axis. We've got a vertex at 0k, and we know that on the right of the vertex we go downhill, so the line has equation y is k minus 2x, and on the left of the vertex we go uphill, so it's k plus 2x. This should be symmetric about the y-axis. We can also determine the cuts on the x-axis by setting y to be 0. So 0 is k minus 2x, so 2x is k, which means that x is k over 2. And on the other hand, k plus 2x is 0, so 2x is minus k, leading to x being minus k over 2. So the cuts on the x-axis are at minus k over 2 and k over 2. Now the second graph is the modulus of 2x minus k over 3. So I will follow a similar approach. We've got y is the modulus of 2x minus k over 3, which can be split as 2x minus k over 3 if 2x minus k over 3 is greater than or equal to 0, or minus brackets 2x minus k over 3 if 2x minus k over 3 is less than 0. So this can be simplified into 2x minus k over 3 if x is greater than or equal to k over 6, or minus 2x plus k over 3 if x is less than k over 6. So it's easy to see that the vertex is when x is k over 6. When x is k over 6, all of this is 0, and therefore y is 0. So once more, I will draw my pair of axes. I will put my vertex at k over 6, 0, and then I will draw the lines. So k over 6 is somewhere here. On the right, we go uphill. The equation is y is 2x minus k over 3. And on the left, we go downhill. So the equation is y is minus 2x plus k over 3. Obviously, the cut on the y-axis is at k over 3, and this completes the first part. Now, in the second part, we need to find, in terms of k, the solutions to this equation here. so it actually makes sense to combine the two together. So I will draw this onto my second graph to find the points of intersection. We had the vertex at K and it was going downhill. The equation was K minus 2x, so this is K minus 2x. The vertex was at K. Notice that this has a gradient of -2 and this has a gradient of -2, so these two are parallel. And similarly, this branch here was the line with the equation y is K plus 2x. So these two lines are parallel as they have the same gradient. So this makes it easy for me to see that the points of intersection, the solutions to the given equation, are simply the point here and the point here. So I will start by equating K plus 2x with the minus 2x plus K over 3. I will multiply throughout by 3 to get 3K plus 6x is minus 6x plus K, leading to 12x is minus 2K, and therefore x is minus K over 6. Alternatively, I will equate K minus 2x with 2x minus K over 3. I will multiply by 3 to get 3K minus 6x is 6x minus K. This leads to 4K is 12x, so we get that K over 3 is x, and these are the two solutions to the given equation. In question 7, we've got that x is 6 sine squared 2y, and we need to show that the y, the x can be written in this form. I will start by writing x as 6 brackets sine of 2y squared. So dx dy will be 6, and then we get the power down, we deduct 1 from the power, times the derivative of the bracket. The bracket is the sine of 2y, and its derivative will be 2 cos 2y. So this leads to 24 sine of 2y cos 2y. So we need to go from an expression that involves y to an expression that involves x in order to match eventually the printed answer here. So starting from the original relationship, we can say that x over 6 is equal to sine squared 2y. So root of x over root 6 is sine of 2y. I will draw a triangle here. So if the angle at the bottom is 2y and it's a right angle triangle, then sine of 2y is opposite over hypotenuse. So I could use Pythagoras theorem. This is 6 minus x square root, which means that the cosine of 2y is simply the adjacent 6 minus x root over the hypotenuse, which is root 6. So dx dy will be 24 times root x over root 6. This is the sine of 2y from here, times the cos of 2y, which we just found to be root of 6 minus x over root of 6. This simplifies to 24 square root of 6x minus x squared over 6, which is 4 root of 6x minus x squared. And the last thing that remains to be done is to go from a dx dy to the dy dx expression, which is 1 over 4 root of 6x minus x squared. In question 8, we've got a formula for n in terms of t. N is the number of fish, t is the number of years after the start of the study. In part A, we need to find the number of fish at the start of the study. So this simply means that we set t to be 0. So when t is 0, we have that capital N is 600 e to the 0 over 2 plus e to the 0, which gives an answer of 200 fish. In part B, we need to find the upper limit to the number of fish in the lake. So this means that I will consider the value, the behavior of capital N as t tends to infinity. So as t tends to infinity, N will tend to 600 e to the 0.3 t over e to the 0.3 t. What we are saying here is that as t grows larger and larger, the 2 is insignificant and all the power is withheld within the exponential terms. So this simplifies to 600, and 600 fish is the upper limit for the population. Then in part C, we need to find the time after the start of the study when we've got 500 fish predicted to be in the lake. We need to give answers in years and months to the nearest month. So in other words, I have to solve 600 e to the 0.3 t over 2 plus e to the 0.3 t is equal to 500. I start by cross multiplying to get 600 e to the 0.3 t is 1000 plus 500 e to the 0.3 t. So 100 e to the 0.3 t is 1000. So e to the 0.3 t is simply 10. I will now take ln of both sides, leading to 0.3 t is ln of 10. So t is 1 over 0.3 ln 10. If I plug this on the calculator, is 7.675 ... So it's 7 years and 0.675 of a year. This means that we are looking at 7 years and 8 months. In part D, we need to show that the derivative can be written in this form. So I will start by rewriting the expression for capital N. We had N is 600 e to the 0.3 t over 2 plus e to the 0.3 t. So dn dt, we start by differentiating the top. I'm using the quotient rule here. So 600 times 0.3 e to the 0.3 t, and I keep the bottom, minus keep the top, 600 e to the 0.3 t times the derivative of the bottom, which is 0.3 e to the 0.3 t, and all over the bottom squared, the 2 plus e to the 0.3 t squared. So I can proceed. 600 times 0.3 is 180, so 180 e to the 0.3 t brackets 2 plus e to the 0.3 t minus 180 e to the 0.6 t, all of it over 2 plus e to the 0.3 t squared. I proceed further. I get 360 e to the 0.3 t plus 180 e to the 0.6 t minus 180 e to the 0.6 t over 2 plus e to the 0.3 t squared. Now the e to the 0.6 t terms cancel out, and therefore this leaves us with a final answer of 360 e to the 0.3 t over 2 plus e to the 0.3 t squared, and therefore the constant a was 360. In the final part, when t is capital T, the dn dt is 8, and we need to find the value of capital T to 1 dp. So we are asked, in other words, to solve the expression we just found for the derivative. So 360 e to the 0.3 capital T over 2 plus e to the 0.3 capital T squared is equal to 8. I will start by letting w be e to the 0.3 t, which means we've got 360 w over 2 plus w squared is equal to 8. Now I will cross multiply to get 360 w is 8 times 2 plus w squared. The 8 with the 360 simplified to leave me a 45 on the left. So I get 45w is 4 plus 4w plus w squared. So 0 is w squared minus 41w plus 4. I will be using the quadratic formula to find the values for w. So we have that w is minus b plus minus b squared minus 4ac square root over 2a, so it's 2 times 1. This leads to solutions for w of 41 plus minus 3 root 185 over 2. So we either have that e to the 0.3t, the w is 41 plus 3 root 185 over 2, or that e to the 0.3t is 41 minus 3 root 185 over 2. Now to undo the exponential, I take the ln of both sides. So 0.3t is ln of 41 plus 3 root 185 over 2. And if I divide by 0.3, this leads to t being 1 over 0.3 ln of 41 plus 3 root 185 over 2, which gives an answer of 12.4 years to 1 decimal place. I will also consider what happens on the right hand side here. So I take ln's, I get 0.3t is ln of 41 minus 3 root 185 over 2. I can divide by 0.3. t is 1 over 0.3 ln of 41 minus 3 root 185 over 2. And this gives an answer of t being minus 7.7, which is obviously rejected. It's not valid since t is time and has to be positive. So our final answer will be capital T is 12.4 years. In question 9, we start off by being asked to express 12 sine x minus 5 cos x in the form r sine x minus alpha. So I will write 12 sine x minus 5 cos x is r sine x minus alpha. I'll be using the addition formula, so this will be r sine x cos alpha minus r cos x sine alpha. I will be equating the sine x terms and then the cos x terms, and this will give me two equations. So we have that 12 is r cos alpha and 5 is r sine alpha. So 12 over r is cos alpha and 5 over r is sine alpha. I like to draw a triangle here, and we've got alpha, the cosine is the adjacent over the hypotenuse, and the sine is the opposite over the hypotenuse. So Pythagoras will give us that r is 5 squared plus 12 squared square root, which gives an answer of 13. We can also see that tan alpha is 5 over 12, which leads to alpha being 0.395, and therefore we've got 12 sine x minus 5 cos x is equal to 13 sine of x minus 0.395. That was part A. Now part B, we've got the function g defined here. Obviously we've got similarities with what we have here. We can see that the x has been replaced with 2 theta minus pi over 6, and we're being asked to find the minimum value of g of theta and the smallest value of theta at which this minimum occurs. So I will start by saying that we've got g of theta, which can be written as 10 plus 13 sine of 2 theta minus pi over 6 minus 0.395. Now we know that sine of any angle varies between plus minus 1. So 13 sine will be varying between plus minus 13. And therefore it's obvious that the minimum of g of theta will be at 10 minus 13, which is simply minus 3. Now this minimum will be at 10 when sine of 2 theta minus pi over 6 minus 0.395 is negative 1. So we are asked to solve sine of 2 theta minus pi over 6 minus 0.395 is equal to negative 1. My principal value is shift sine of negative 1, which is minus pi over 2. And therefore we have that 2 theta minus pi over 6 minus 0.395 is equal to minus pi over 2 plus 2 pi k. I can rearrange to leave 2 theta on its own. So 2 theta is minus 0.652 plus 2 pi k. So dividing throughout by 2 leads to theta being minus 0.326 plus pi k. And the first positive solution is when k is 1, which gives me theta to be 2.82. And the last part, we've got the function h defined by this expression here, and we need to find the range of h for 2 marks. So once more, we've got similarities with the opening part, with part A of this question. So we've got that h of theta is 10 minus 12 sine theta minus 5 cos theta squared. I will replace the bracket with 13 sine of theta minus 0.395 all squared. Now I could expand this. We've got 10 minus 169 sine squared of theta minus 0.395. And we do know that the sine squared of any angle must be varying between 0 and 1. It cannot be negative because it's something squared. It cannot go beyond 1. So if I multiply by negative 169, that means that the sine squared of theta minus 0.395 will be between minus 169 and 0. I could then add 10, so 10 minus 169 sine squared of theta minus 0.395 will be between 10 and minus 159. So what we did here was that we reconstructed h of theta by starting from sine square being between 0 and 1. So our final answer is that the range of h will be between minus 159 and 10.